Okay, good morning, afternoon, or evening, everybody. Welcome to the Easy Sentinel-1 Radiometric Terrain-Corrected, or RTC, Products with ASF's Beta Toolbox webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we're going to go ahead and get started. First, what I'd like to do is go over a few logistics for today's webinar. To ensure the best audio experience, participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you should find that located on the lower right-hand side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted both to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a couple of days of completion. Once this has been completed, what I'll do is I'll send an email to all registrants with the recording links. Regarding timing, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and live demonstration and an additional 15 minutes for the question and answer period. Once our speaker has finished with his presentation, we will transition to a final set of optional polling questions. And then we'll give these about 3 to 4 minutes or so, and from there move directly into the Q&A period. Depending upon the volume of questions that are received, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line. Today's speaker is Andrew Johnston. He is a senior software engineer at the NASA Alaska Satellite Facility Distributed Active Archive Center, or ASF DAC. He and his colleague Tony Abbey will begin today's webinar with an introduction to the ASF DAC, background information for the ASF Beta Toolbox development, and this will be followed with a brief discussion of the benefits of the command line radiometric terrain correction, or RTC tool, which is the focus for today's webinar. From there, we will transition to a demo that takes participants through the Docker installation, and then once this demo has completed, our speaker will talk through the Sentinel-1 Toolbox RTC command line tool demo. Finally, we will wrap up today's webinar with next steps and some options for user feedback. With that, it is my pleasure to introduce today's speaker, Andrew Johnston. Andrew?
I'm Andrew Johnston. I'm a senior developer with the Alaska Satellite Facility, and I'm a member of the development team behind the tool we'll be demoing today.
And I'm Tony Abbey, product owner at the Alaska Satellite Facility.
So, brief introduction to our presentation. We're here today to demo a preview release of our new Advanced Products Toolbox that's actively under development at ASF. So the Alaska Satellite Facility is invested in creating advanced value-add products on top of remote sensing data from the Sentinel-1 satellite mission. Those products include data recipes for things such as radiometric terrain correction, interferometry, change detection, and time series. The tool we'll be demonstrating today is our initial release attempting to put the first of those advanced products, radiometric terrain corrected Sentinel-1 images, in the hands of the science community, packaging them up in a way so that users can generate those products on their own machines in their own computing environment in as simple and straightforward a manner as possible. As I mentioned, this is a product that's under active development. We're very eager for your impact. If you think these products or these tools will be of use to us, please email us your input and we'll give you some more information on how to give us feedback later in the presentation. First, a few background slides. We are the Alaska Satellite Facility. We are part of the Geophysical Institute at the University of Alaska Fairbanks, and our mission is to make remote sensing data accessible. As part of that mission, we are one of 12 NASA Distributed Active Archive Centers, or DACs. Each DAC is responsible for downlinking, processing, archiving, and distributing NASA remote sensing data to scientific users around the world. The ASF DAC specializes in synthetic aperture radar imagery from satellite missions such as Sentinel-1, ALOS, going all the way back to the CSAT mission in the 1970s. And all data sets provided by the Alaska Satellite Facility are easy to access and free to use under NASA's free and open data policy. So this tool specifically deals with the Sentinel-1 mission and its corresponding data set. Sentinel-1 is a two-satellite constellation operated by the European Space Agency, first launched in 2014. Each of those satellites carries a C-band radar sensor that provides all-weather day and night imagery of the Earth. And the satellite constellation's global coverage and 6-day repeat cycle provide support for applications requiring long time series. The sensors on board these satellites are able to detect centimeter scale deformation of the Earth, and having the same picture of the Earth from the same point in space every 6 to 12 days going back for the last 5 years is an incredibly powerful tool for many science applications, in particular those in land monitoring, marine monitoring, and emergency response fields. And thanks to an agreement between NASA and the European Space Agency, all of the data from the Sentinel-1 mission is available for download and access from the Alaska Satellite Facility. The tool we'll be demoing today specifically performs a process known as radiometric terrain correction. Radiometric terrain correction, its intent is to correct distortions introduced by variable topography on both the position of the target and on the brightness of the radar return. And the intent is to produce a superior product for science applications. So if you look at the figure in the lower left, spaceborne radar doesn't look straight down at the Earth. It looks to the side, as you can see in the diagram. That produces some geometric artifacts that need to be corrected for. If you'll see along the ground, the peak of the mountain is roughly equidistant between the base of the mountain on either side. But since the peak of the mountain is at a higher elevation, it's the reflection of the radar beam back to the satellite arrives back at the satellite only shortly after the beam that's reflected from the near base of the mountain. As a result, you can see in the image plane, which is the output product and radar image that the sensor will provide, the peak of the mountain appears to be much closer to the near base of the mountain than it actually is on the ground. That's the distortion related to the position of the target, and we can see that in the before and after image in the lower right. In the before image, the mountains, particularly the ones on the left side of the image, are dramatically skewed to the left towards where the satellite was, where it took the image. And in the corrected image, they're standing straight up. And the intent of this correction is to line the features in your image with the actual features on the Earth, which is particularly important for applications where you're working inside of a GIS environment. Additionally, not only is the position of the target influenced by the elevation changes, so is the brightness of the radar return. Referring back to the diagram in the lower left, all of the radar signal reflected back from the near slope of the mountain is compressed into a relatively small area of the image in the image plane. As a result, the image appears brighter in that on the near slope than it would otherwise. That's the radiometric half of radiometric terrain correction is an attempt to address that distortion in the brightness as well. And the intent of this processing is to produce a GIS-ready, science-ready product that's accessible to the science community. Unfortunately, the images delivered for the Sentinel-1 mission from ESA have not been terrain corrected out of the box. So science users with a need for terrain-corrected imagery are left to do that processing themselves. Enter the preview release of ASF's new Advanced Products Toolbox. Our intent is to provide you a software tool that will produce GIS-ready Sentinel-1 radiometrically terrain-corrected products. We're optimizing this tool for one-step processing. Our intent is that after a simple install, you can issue one simple command with the name of the scene or granule you'd like to process, and we return you the final corrected product. The tool we'll demo today supports both single-look complex and ground-range detected Sentinel-1 products. We're leveraging the Sentinel-1 Toolbox from ESA under the hood to do the processing and corrections. That's a well-known and popular tool in the radar community. So we're using tools people are already familiar with and trust under the hood. As of today, our tool is supported on Linux operating systems. Our intent is absolutely to make it available on Windows and Mac OS as well. We realize that's where the majority of users in the science community are going to be working. That's a high priority for future development. If these tools and products are of interest to you, please give us that feedback. And we're eager to work with you to bring it to other operating systems as well. The specific products that this tool produces, here are some of the technical details. The output images are in GeoTIFF format. Pixel spacing is set to 30 meters. The pixel values in the images indicate gamma naught power. The images have been projected into the UTM coordinate system, and each output GeoTIFF is accompanied by an ArcGIS compatible metadata file. These are some of the details of RTC correction on which reasonable people can disagree. But we found this particular set of parameters provides a quality science product that should be applicable to a large number of science use cases. All right. So before stepping into the demo, I'll hand things over to Tony briefly to speak to why we think a tool like this has value to the community.
Thank you, Andrew. The question is, what makes this tool attractive to end users? Well, as this slide states, it is a very easy tool to use and allows for RTC processing in unlimited quantities. It includes an easy Docker install with no requirement for additional software or libraries to be downloaded and configured. Everything you need is in one place. On top of that, setup and installation only takes 5 minutes. Installation should actually take less than 5 minutes, but we understand that bandwidth and computers vary. Therefore, 5 minutes should be the maximum amount of time required to get you set up. Lastly, allow me to remind you of the key features that this tool includes. The first is single command processing. Second, default settings for the RTC product are pre-selected for a standard product. And third, options are available for adding ancillary files such as layover shadow mask. So in summary, this is most definitely an easy Sentinel-1 radiometric terrain correction tool that produces analysis-ready products.
Next, we'll move into the demonstration portion of this webinar. Here's a brief summary of the steps we'll step through. First, we'll preview an uncorrected product, a Sentinel-1 scene straight out of the box from the Alaska Satellite Facility in a GIS environment. We'll call out some of the features related to some of the geometric distortion we want to correct. Then we'll step through a demo of installing the Advanced Products Toolbox in a Linux environment. Third, we'll step through running the tool to perform the RTC correction on our example product. And then finally, we'll review the corrected product back in the GIS environment. I have ArcGIS Pro open on my machine. This is a common GIS environment in the industry. We're looking at the world imagery map layer that comes bundled by default with ArcGIS. And overlaying on top of that is the Sentinel product we're going to correct as delivered out of the box from the Alaska Satellite Facility. This is a ground range detected Sentinel-1 product for a dual polarization scene. We're specifically looking at the VH image. And if we toggle between that and the underlying map, the main feature we want to call out is the location of the crater at the top of the mountain. You can see they're not lined up on top of each other when we flicker between the two images. Zooming in a little closer, this is a consequence of the dramatic elevation change from the mountain. You can see that the coastline of the island agrees between the base layer and the satellite image, but the location at the top of the mountain is displaced by almost 3 miles. And that's the distortion that radiometric terrain correction is intended to account for. So next we'll transition to a demo of installing the tool. Jennifer, if you could pull that step up, thank you. Short demonstration. On the left, we have an excerpt from the user guide for our tool. The link to the user guide should be available in the related links section of your interface, and so you should be able to review it later on your own. But we're specifically calling out the system requirements and the installation instructions for an Ubuntu Linux environment. And on the left side of the screen is the terminal session into a Linux machine where I'll be stepping through the installation. So first, calling out some details of the system requirements. Today, we are supporting this tool on both Ubuntu and CentOS Linux. These tools will absolutely run and can be installed in other environments, but we don't have that installation as turnkey as we'd like. Again, if you'd like access to these tools on Windows and Mac OS, please give us that feedback. We're eager to put in that work and bring these tools to a place where they're accessible to you as well. Working with Sentinel-1 imagery can be somewhat processing intensive, so your computer will need at least 16 gigabytes of RAM available and up to 20 gigabytes of available hard disk space. All right, so stepping into the installation instructions, we're using a software tool called Docker to manage packaging and distribution of the RTC tool. Docker is a way of bundling all of the software requirements for a particular recipe into one place. One of the common difficulties in working with SAR imagery in particular is the vast array of software tools needed to do much of the processing. In this case, the Sentinel-1 Toolbox from ESA, as well as GDAL, the Geospatial Data Abstraction Library. Our installation, we're using Docker, the software, to manage installing those other tools for you. And so it's one simple installation step for you, and you can get straight to producing terrain-corrected images. So we'll go ahead and step into the demo. So installing Docker in a Linux Ubuntu environment is the same as installing any other software package. It's 2 simple commands. The first is an apt update that simply updates the list of software that's available to be installed. And the second command is an apt install that will install Docker itself. And again, these steps are as simple as copying and pasting the commands out of the user guide. That's step 1 completed. Docker is now installed. The only other step is I do need to give my Linux user permission to run Docker commands. I do that by adding myself to the Docker user group in step 2. Again, a command to copy and paste. And then in step 3, in order for that permission change to take effect, I do need to log out and log back into the machine. So I'll exit to log out. I'll reconnect. That's step 3 complete. And now everything should be good to go. In step 4, we'll validate the installation with a simple docker run hello world command, which will dump a fair amount of text to the screen, but the magic words we're looking for are right there. Hello from Docker, your installation appears to be working correctly. That means we're set up and ready to go. That's step 4. And then the final step, step 5, is to download the script we'll be using to invoke the RTC processing itself. I do a directory listing. I have that script sitting in my current directory, and that's the entire installation process. In about 2 minutes, we're set up, we're ready to go, we're ready to start processing individual Sentinel-1 scenes. So next we'll transition to a demo of actually using the tool to perform correction on our sample product. All right, this demo picks up right where the last one left off. I'm still logged into my Linux machine. The tool's been installed, and the script I'm going to execute to run the processing is sitting in my current directory. All of this processing to get a terrain-corrected Sentinel-1 product is one simple command now. I simply provide it the name of the Sentinel scene which I want to process. All right. Once we kick that off, the first thing that's going to happen is it's going to go through the download of the software package the very first time you run the tool. This is where it's pulling in those dependencies such as the Sentinel-1 Toolbox and GDAL. This step should only occur the first time you run the tool. Subsequent runs would skip this step unless there are actually updates to the software. As soon as the package is downloaded, the tool will next attempt to download that Sentinel scene from the archive at ASF. Just like downloading any other data from any NASA DAC, that does require me to provide an Earth Data login, username, and password. So I'll provide those. The granule will begin downloading. And at this point, the process is completely hands-off. I provided the name of the granule, my username and password, and I'm on my way to an RTC corrected product. After the granule is downloaded, we will prepare a digital elevation model. RTC processing depends on a digital elevation model to tell us the height of the Earth at each place in the image so that we can do the appropriate corrections. So when we fetch a digital elevation model, the script will inspect the scene that you are processing in particular and find the best digital elevation model from either the National Elevation Dataset or NED-DEM or the Shuttle Radar Topography Mission or SRTM-DEM. It'll attempt to find the best combination of both coverage of your scene and resolution of the DEM. Again, all handled for you in a seamless process. Once the granule and the digital elevation model have been downloaded, we'll step into the actual processing. So here we're invoking various commands provided by the Sentinel-1 Toolbox. First, we'll apply the precise orbit file provided by ESA. We will calibrate the product. Next, we'll perform a speckle filter. Radar imagery at the pixel level tends to come back with a salt and pepper speckling. This operation is an attempt to smooth out and correct some of that. Once the speckle filtering is done, we'll perform a quick multi-look operation. Multi-looking also attempts to smooth out some of that speckling. And then the final two steps will do the actual radiometric terrain correction. The first of those steps is terrain flattening. This handles the radiometric portion of the correction. That corrects the brightness of the pixels to account for the elevation changes. I will make a note that this demo will run through in about 4 minutes, but this footage has been time-lapsed, so you can see the entire execution in a short amount of time. Your mileage won't vary depending on the particular computer you're running this on, the scene you're processing, and the quality of your internet connection. You can process granules as quickly as 5 or 10 minutes, but on many machines, that processing could take up to 1 or 2 hours for large scenes. And the final step is terrain correction. This is what's going to move the mountaintop back into its correct place on the Earth. Once all the correction has been done, we'll generate our final output products as cloud-optimized geotiffs. Again, this was a dual polarization product. So the original product from the ASF satellite facility contained 2 geotiffs, and the RTC corrected product, we output a corresponding corrected TIFF for each of those. As the last step, we provide you with your ArcGIS ISO standard metadata file. And when I do a directory listing, we can see that it was that easy. One command, provide a granule name, a username and password, and I now have RTC corrected copies of that image with their corresponding metadata files. If I had another scene I wanted to process, it's as simple as rerunning the same command with the new name of the granule. No need to download any of the products up front, no need to clean up anything after the fact. Just get straight to your corrected product and put it to work for your science application. So next we'll transition back to my GIS and take a look at the corrected product. All right, so we're back to ArcGIS, looking at the Big Island of Hawaii. So first I'm going to put the original uncorrected product back up to remind us where we started. So there's the uncorrected product, again with the mountaintop displaced by up to 3 miles. And next we'll overlay the terrain corrected product produced by our tool. So in particular, if we zoom in a little, I again call out that the coastline of the island still corresponds with the base layer, but now post-correction, the top of the mountain also corresponds with its actual location on the Earth. And we'll flicker between the corrected product and the uncorrected product. Again, to show that dramatic difference. That completes the demonstration. We hope that's a tool and a product that will be exciting to the science community. We'll step through some slides that speak to a few more details about the tool. So first, the demonstration I gave just ran the tool with all of its default settings. Again, our intent is to provide a simple one-step solution to getting you to an analysis-ready product. We think that default product is a good fit for many science applications, but we do provide you some command line options to adjust a couple of things. So first, we do let you pick how we go about preparing the digital elevation model that's used. The default setting that I demonstrated will automatically download either a geoid-corrected NED or SRTM DEM from the Alaska Satellite Facility based on the best combination of coverage for your scene and resolution of the DEM. However, we do allow you to override that behavior and instead use the built-in Sentinel-1 Toolbox support for the SRTM 1 arcsecond DEM. Second, we do provide 2 flags to include additional output products after processing is completed, so specifically for a layover shadow mask image, as well as a projected local incidence angle. We don't produce those output files by default because they may not be applicable to your use case, but if those additional products are of value to you, it's a simple yes or no switch to have them included in your processing. And the final clean option is another flag you can set to help remove border noise in some older ground range detected products. This is similar to the remove GRD border noise operation provided by the Sentinel-1 Toolbox. So that demo describes where we're at with the tool today. We'll be providing you with a link to the user guide. You can immediately go out and install it and try it and step through the same steps that you just saw me demo here. This tool is under active development. We'd love to hear your feedback on what direction we should go next. At a high level, here are some of the things we expect to work on. We would definitely like to improve support for both Windows and Mac OS, expand accessibility to this tool to additional platforms where we know the science community is doing a lot of their work. We'd like to add support for additional Sentinel-1 data products beyond radiometric terrain correction. For example, products such as interferometry, time series, and change detection. And we'd like to build in support for bulk processing of products in cloud computing environments such as Amazon Web Services. As I mentioned before, working with Sentinel-1 and radar data can be fairly compute intensive. These can be long operations to run on your own computer sitting on your desk. Cloud services such as Amazon Web Services provide you the opportunity to process many products at once, all in parallel, but does require some of a learning curve. We'd like to bundle that work into this tool to provide an easy step into the cloud for users that may not have worked in the cloud before. So those are our current ideas for future development. We'd love to hear your thoughts as well. And I'll transition to Tony to let you know how you can provide us that feedback.
We encourage you to try this very easy process out yourself. The slide shows you the URL for the user guide, but if you're unable to capture that, email us and we would be happy to send you the link. Please contact uaf-asf-udg@alaska.edu. That's UAF for University of Alaska Fairbanks, ASF for Alaska Satellite Facility, and UDG for User Development Group. We also aim to make this tool as user-friendly as possible, and we want to incorporate your feedback. If you would like to see a feature added, please reach out and let us know. You can do this by either filling out the Google form located on the screen or email uaf-asf asf.udg@alaska.edu. Lastly, if you would like to explore the data and services that the Alaska Satellite Facility provides, please go to www.asf.alaska.edu.
And all of these links should be available in the related links section of your interface. That concludes today's demonstration. Thank you all for attending. We look forward to hearing from you, and I'll transition back to Jennifer.
Okay, thank you, Andrew. So at this point, what we'll do is we'll transition to a final set of polling questions. We finished a little bit early, so we'll give these about 3 to 4 minutes or so, and then from there we'll transition to the Q&A, and then there you will find the links that were just mentioned on the last slide and the presentation content for download that includes the slide deck, as well as the installation demo and the demo of the tool itself. So you'll have all of that information available, and I'll speak to that in just a few minutes when we transition to the Q&A. All right, thanks everybody. We'll give these about 3 to 4 minutes or so. All right. Okay, everybody, we're going to give these polls just another minute or so, and then from there we'll transition to the Q&A session. Okay, everybody, at this point we will transition to the Q&A period. And we did have a question earlier. Just give me 1 second. Okay, so the first question was asked, is RTC only for the Alaska DAC?
So radiometric terrain correction is a process that applies to just about any spaceborne radar imagery. The tool we demoed today is specifically for these data collected from the Sentinel-1 mission.
Okay, thank you, Andrew. And then the next question is, how is it possible to change the DEM, for example, after GDEM instead of SRTM used in the demo?
What we've demoed today is either let us pick for you from between the NED DEM or the SRTM DEM, or allow you to override that and use the SRTM DEM directly. If you think other DEMs will be a good fit for your use case, please give us that feedback. And that's something we can look at for future development.
Okay, thank you, Andrew. Are there additional questions? Let me take a look here. Does anybody have any additional questions? Okay, well, while we're waiting to see if there are additional questions, you'll note that directly below the Q&A pod, there is a useful links resources pod. So if you were to click on either of those, review the user guide, any of those entries, you'll be sent directly to the link associated with that entry. And then just below that, you'll see today's presentation files, including both of the demos, as well as the slide deck from today's presentation. So we'll give it one more look for questions here. And if there are no further questions, what we will do is we'll log off from the audio component, but we will leave the virtual meeting space open an additional 10 minutes or so. If you think of any questions, feel free to please jot those into the Q&A pod, and then our speakers can address those offline with you. All right, let's take another look. Any additional questions? All right, well, with that, I would like to thank our speakers today, Andrew Johnston as well as Tony Abbey, for their presentation, and to thank all of you for your participation. And I'll check at one final look, and with that, we will log off from the audio component. And thanks again for joining us. All right, everybody. Goodbye.